So now we come to spans, which is after subspaces and the subspace test theorem. It's this idea of querying forth, how can we understand more deeply what makes a vector space tick, sort of its internal properties. The idea of a spanning set begins to address this issue. Okay, so let's go and see what, so let's look at, let's say, let's say I had a set that was like this. Okay. So there's a set of all the vectors of this form, right? Now, one thing I can do with this that we've done before is that this might be what you get as a solution of some linear system, sort of vaguely. You can sort of see after you've found that, well, maybe I should just make this more like that. Let's say 2y plus z, and then this would be y and z. So it's like the equation might have been x minus 2y minus z equals 0, and then I'd solve for a free variable in terms of the leading variables y and z, and I get this form. So we're not so concerned with where this came from as what I want to do with it. Well, if you have gotten this, and this is what I've asked you to do when you've written down solution sets, is to pull out the vectors. Like what I do is here, I pretend z is 0 and write y times 2, 1, 0, right? That gets the 2y and the y. Then I pretend y is 0 and write up here 1, 0, 1, and such that y and z are real numbers. Okay? This is a process you've been doing in the homework assignments, right? And this technique of pretending that y is 0 is just a tactical maneuver to get you to sort of undo the this vector multiplication addition, where I've pulled the variables out here and I'm multiplying by constant vectors. Now, this is an example of a span. So if I have a set here, so let's take this let's call, let me see, since it's the text, let me call this, I'll leave it as S. Let's say that I have the set T, which equals just these constant vectors, 2, 1, 0, 1, 0, 1, right? So I've just taken out the constant vectors here as a set T. So what I say is, what I write is, if I'm given a set T like this, then I define the span of T to equal S. So it equals, say, y times 2, 1, 0 plus z times 1, 0, 1, such that y and z result. So this is a span. A span is just an expression written like, it's like the span is just all the linear, if I'm given two vectors, say, it's all the linear combinations of those vectors. So given a set of vectors, I can make the extra set, which is all the linear combinations of those vectors. So here, so that we say that T is a spanning set of or for S, right? So typically T is just, we just need two vectors here, right? So then we can start then from any two vectors or any three vectors or four vectors and from the span of that set just by taking all the linear combinations. So given any set of vectors, say T, the span of T is all linear combinations. All linear combinations of vectors in T. So, for example, if I have the set U equals 1, 2, 2, 1, then the span of U would equal the set x 1, 2 plus y 2, 1, such that x and y are members of R. Okay, so so I have just constant vectors here, no variables, and I take the span of U as just the free variable times 1, 2 plus a free variable, unrestricted variable times the second vector, and that would be the case. It doesn't have to be just two; it could be any number of vectors, right? Okay, that's the idea of a span. Okay.
How do you know to use the free variables x and y?
You don't, because the free variables here are just placeholders.
Okay.
They're just, I could use other ones. I could say this is the same set. See, because x and y can be, they're not really, we've always used them as free variables. So I could just call this R 1, 2 plus S 2, 1, such that R and S are members of R. So these are the same sets. They're just different ways of naming the same sets. This is, we've this extra piece, so we've taken a solution set, and what I've had you do is form the span where the numbers in front are the free variables. But they don't actually have to be free variables. And in fact, the span, if I change these names, doesn't really matter. I mean, we might lose information about what the connection is to the linear system, but this set of vectors is the same as this set of vectors. It's just that we might not know what R and S are in terms of a linear system. Okay, so you've been creating spans all the way through from the beginning, and I've done that because a lot of people have trouble with the idea. So hopefully having now the process you've done is taken a set and expressed it as a span, right? You've been given some set, the solution of a homogeneous linear system, and then you've rewritten that by solving the linear system, finding the free variables, and writing it in this way where you have to factor out all the constants as a span. Okay, so the point is that so this is just sort of another way of looking at that. Like here's the example in the text when I have a vector of a subset of R3C where there's a linear system here of one equation. This could be a full linear system. We could have like two equations here that we'd have to solve, and then we go and solve it, and we'd find the free variables, and then we would write in, eliminate the leading variables, and then you can see that I've written it here, where it gets written as a span of Y and Z, okay? And here's no result. Here's a subspace L of 2 by 2 matrices, subject to this condition. Okay, well, I solve this condition. Think of this as a linear system in the variables A, B, and C, and that the leading variable is A, and B and C are free variables. And then you've eliminated the leading variable here, and then done this thing where you pull out B times a constant matrix and C times a constant matrix, which have been thought of as vectors. So then L is the span of those two matrices. Okay. Now, so here's the definition. the span of a non-empty set S, S1 to Sn, any number of a vector space, is the set of all linear combinations of the vectors in S. So here's the span. It's got all the C1s and the CNs are any real. They're sort of like the free variables. But we're just defining it directly as a span without reference to a linear system. And then this extra definition, the span of an empty set is the zero subspace. Right? So if I have a set S, if this Fs was empty, what's the span? Well, it's going to be this is weird, but it's sort of like one of these conventions that gets sort of works to make everything else easy to state without exceptions. Okay. There's immediate consequences that here is, and here's sort of the motivation. Here's what the idea, sort of the consequence of this definition is. Okay, so let's take S as a subset of a vector space, right? This can be any subset, right? Well, the point is that the span of S, right? Well, because it's a subset of the vector space, and because the vector space, any two vectors, if I take any linear combination in S, since if S is just two vectors, it's not going to be in S, but it will be in V. So the span of S, all the linear combinations vectors, will be a subset of V. Now, then if we apply our subspace test theorem to this, we have to form any linear combination of the span, right, of the vectors in the span, and check that it was inside the span. But that's just saying, if I take, let's say that I had S was just equal to 1, 2, 2, 1, right? And that means that V was equal to RC2, as an example. Then the span of S was given above. It's this thing here. The span of S is that thing. Just the name's U up here, down it says. Well, the question is the span of S a vector space? Well, I'd have to check that R times A12 plus B21 plus S times C12 plus D21. I have to check that this thing was also in the span of S. But you can see that, well, if I multiply in this R, I'm going to get a linear combination of 1, 2, and 2, 1. And over here, I multiply this in, I'm going to get 1, 2, and 2, 1. Then if I collect the terms, I'm just going to get something like R times A plus S times C times 1, 2 plus R times B plus S times D times 2, 1. So the point is, a linear combination of linear combinations is just going to be a linear combination of the same vectors. I can't just so that as a result, this thing is a subspace. In general, that's the result. The result is the span of any subset of a vector space. So I take any subset. Span of S is always a subspace. So every span is a subspace, right, of the vector space V. Now it turns out that V, and also any subspace is also a span. So why is that? Well, if I take the subspace, let's say V subset of W, let's say this is V is a subspace, right? Well, I want to write that as a span. Well, what I can do is I can point out that V equals the span of V. I take every vector in V as my set of vectors. I can say, well, For any vector v, it equals to 1 times v. Right? So this is a vector in v, this is a vector in the span of v. So any vector in the span of v is in v. So it's going, so the vector space, the point is, any vector space is a span, any span is a vector space. So that's the content of this thing here. The span of any subset of a vector space is a subset, is a subspace. It is a vector space of that space, and then any subspace is the span of some subsets. So you can sort of say any subset of a vector space is a subspace if and only that subset is a span of some subset. Well, that's like a tongue twister, right? You know, there's too many S's, but just see if you can repeat that 5 times without making a mistake, right? Okay, so but the point is that vector spaces, every vector space is like a subspace because every vector space is a subspace of itself, and every vector space is the span of some set, and every span is a vector space. So this is going to be the core of the idea of getting to what's in. We're going to sort of analyze vector spaces as spans of small sets. We want to sort of see, well, how small can we make the set that spans the space? How big of a set do we need to span a space? So these are sort of the properties we're looking for.